Alright, so in the next few videos, I want to explore what is perhaps one of the most difficult concepts in chemistry for students when they're starting out. This is the part of the basic ideas of chemistry that involves the maths. And it's something which my experience in teaching first year chemistry for over 20 years now would suggest is something that students find very, very difficult to get their heads around first time up. So we're going to try and take it slow, but please be aware that this stuff is really important, and so if you need to go over this a few times, then you should do so, because the ideas we're going to talk about in these next few videos are going to come back again and again and again in later videos, not only in this course, but also in chemistry courses that you're going to see at university if that's where you're headed, right? Now that said, where I want to start is by talking about pancakes. So let's imagine that you wanted to make some pancakes and you go to the internet, as you would, and you try and find a nice simple recipe for pancakes. Well, you may come across this recipe, which is what I did when I went Googling to try and find a simple recipe for pancakes. And the recipe goes like this. It says that if you want to make so-called 3-ingredient pancakes, then you need, perhaps not surprisingly, 3 ingredients. You need bananas, you need eggs, and you need flour. And in particular, the recipe says that you should take 2 bananas and mash them until smooth, and then you mix in 4 eggs and you mix in half a cup of flour. And you mix this all up, and then you pour this into a frying pan or whatever you cook your pancakes in, with a bit of butter presumably, and you can make, according to the recipe, 8 pancakes in this way, right? So this is the sort of thing that you would see in any recipe book, really. You get a list of ingredients, so you get the ingredients and that you need in order to make the thing you're trying to make. You get the relative amounts of each of those things, that in order for that, when you mix those together to get the thing that you want to make, and you get a method. The recipe will tell you what to do in order with the ingredients in order to make the thing you're trying to make. Another way that we could express or write out this recipe is like this. We could say that in order to make 8 pancakes, we need to combine 2 bananas with 4 eggs and half a cup of flour. So we could write 2 bananas plus 4 eggs plus half a cup of flour gives 8 pancakes. And we could write it in this way, right? Where rather than having a list of things and then say mix this with this with this, we just put a plus symbol to indicate that we're adding the ingredients together. And then this arrow indicates that we're going to convert the things on the left-hand side, which are our ingredients, when we combine them and cook them appropriately, into the thing on the right, which is the 8 pancakes, right? And so this equation, if you like, is a way of representing the recipe that we've just seen. And with this recipe in hand, we can do more things. We can say, what if, rather than wanting to make 8 pancakes, we wanted to make 16 pancakes? What if we were extra hungry? We wanted to make 16 pancakes. How many bananas would we need? Well, we would look at the recipe and we would see that in order to make 8 pancakes, we need 2 bananas. So to make twice as many pancakes, we would need twice as many bananas, right? So to make 16 pancakes, we would need to have 4 bananas, right? Or we could say, if I want to make just 4 pancakes rather than the 8, how many eggs would I need? Well, we would go to our recipe, and the recipe tells us that if we want to make 8 pancakes, we need 4 eggs. So hopefully it then follows that if we want to make half as many pancakes, we need half as many eggs. So to make 4 pancakes, we would need 2 eggs, right? And so on. And so in this way, recipes are quite good because they tell you about how you can go about making the pancakes. But we can adapt that recipe for however many eggs or bananas or whatever we have in the kitchen. We know how to do that because we know that so long as we mix our bananas and our eggs and our flour in the correct ratios, we should still make pancakes, right? Now, the number of pancakes may differ, but what we end up with rather is still going to be a pancake. It's not going to be some sticky, weird mess. It's going to still be a pancake. So long as we adhere to those ratios, things should work, right? And so, of course, I'm talking about all of this because this is leading us into the idea of how chemical reactions happen, right? In a chemical reaction, we start with some ingredients, which we would call reactants, and we will convert those into some products. Now, that might be one product or it might be a number of products, depends on the reaction. And a key to writing an equation to describe this chemical reaction not only is knowing what the reactants are, the ingredients, and what the products are, but also to know what the ratios of those ingredients are and the relationship between the number of ingredients of each ingredient and the numbers of the products that we can get out, right? Now, one thing that's important to note is that even though the recipe for our pancakes suggests that you should mix 2 bananas and 4 eggs and half a cup of flour, you do have a little bit of leeway, and you can probably still make something which is kind of like a pancake. But chemical reactions don't work this way, right? There's a video which I sometimes play to in the introductory classes of each year. It's a kind of a music video, and it's about the elements. And the chorus of it says something like a box of paints they can mix to make every shade. So it's referring to the periodic table. And it's suggesting that in the same way that you can take different color paints and mix them to make different shades of colors, if you were painting a watercolor or something, so you can mix the elements together in different combinations to make different types of molecules. And this is true, right? Our periodic table has 118 elements, of which there are about 90 odd that are around in suitable quantities that we can use to make molecules with. And in principle, there's a vast number of combinations that you could have of these different component atoms in order to make new molecules. But we have to follow what Dalton said when Dalton came up with his atomic theory. We talked about this in an earlier video. Remember, Dalton said that when we make, say, a water molecule, then a water molecule must have 1 oxygen and 2 hydrogens. Right? There has to be a fixed number of whole numbers of atoms in your molecule. So you can have H2O, but you can't have H2O 1.5 or H2.3O 0.72, right? You could if you were mixing paints together, right? You put a little bit more of red in with your blue to make it a little bit more purple, and you put more red in and make it a bit different shade, different shade, different shade. You can do this if you're mixing paints, which is why I like the video, the song, but I'm not quite convinced about that part of it because it's not strictly right? Not for chemistry. So if we're going to mix oxygen and hydrogen, we can mix oxygen and hydrogen, but we can only do it with certain ratios of those to get out actual stable molecules, right? So that's one thing. And then the other thing is that it's important to know what that ratio of different atoms is in the molecule you're making, right? Because when you mix hydrogen and oxygen together, for example, you don't just make H2O. You can make H2O2, something called hydrogen peroxide. You can make OH minus, the hydroxide ion, right? You still can't make OH 1.5, but you can make OH or H2O or H2O2, right? And they're all completely different things. And so when we're thinking about how we can combine atoms to make new things and writing equations to describe how that works, we need to be aware that the atoms need to be in whole number ratios. We can't have parts of atoms in our overall molecules, and we have to be very clear what it is that we're making so that we know what that ratio of whole number ratio of atoms actually is, right? So if we're going to write an equation to describe making water, that's going to be different to an equation describing making hydrogen peroxide, right? In the same way, carbon monoxide is different to carbon dioxide. CO is different to CO2, right? You still can't have CO 1.5, but we can have CO and CO2. We can have C2H2, C2H4, C2H6, right? These are all different molecules. So when we're writing equations, we need to have a way to be clear which thing we are making. Now, a common concern that students have is that they're worried that we will say to you, if you mix this with this, what do you make, right? If I mix hydrogen with oxygen, what do I make? And then you don't know. Is it water? Is it hydrogen peroxide? You don't know. By and large, this is never a concern, certainly in the papers that we teach here at Otago, the ones that I'm involved with, because normally what we'll do is we will tell you what it is that you're making. And then, because that's not normally the focus of the questions that we're asking you, right? We're not going to say this plus this gives what, A, B, C, D. But also, so that's the first, right, so that's the first thing. You don't need to worry, and in this course, you won't need to worry about knowing what it is that you've made, right? We're not going to ask you questions like that. But the other thing that I suppose I'm hoping, given what we've talked about in earlier videos, is that you're not going to say this plus this gives an oxygen atom, right? Or this plus this gives NH5 2+, or something like that, right? In the stuff that we've talked about, Lewis structures, and talked about bonding and VSEPR theory and that sort of thing, we've kind of shown you how some molecules are stable and some molecules are not, based on the atoms in the molecules being able to attain these stable octet configurations, right? So that's going to be part, hopefully, of what your thinking is when you're coming to write out equations to describe reactions. By and large, we're going to tell you what it is that you're making, but you should always keep in mind that there's these rules for what constitutes a stable molecule which will apply, right? So if you write nitrogen plus hydrogen, you're going to make NH3 maybe. You can make NH4 plus. You can't make NH6 3- or some other random thing like that, right? These ideas that we've talked about previously still apply to what we're going to talk about now. All right, so to write a balanced chemical equation then, to describe some reaction, which, like I'm saying, is kind of like describing how you make pancakes, then we need three things. We need to know what you're starting with, the ingredients. We need to know what you're making at the end, the products. And we need to know this ratio in which the ingredients are combined in order to make the products that we want, right? When we write our equation, when we're doing it for a chemical reaction, our ingredients are going to be atoms or molecules, and our products are going to be atoms or molecules. And one of the key things about a chemical equation that we need to be looking for when we write one is that all of the atoms that we have, either independent or as part of molecules in the reactants, must all still be there in the products, right? Now, the atoms are going to be attached to different things in the products. That's the whole point of a chemical reaction, right? So you might have molecules, and those molecules will come apart, and then they combine again in different ways to make your products, right? That's completely fine. But we can't gain any atoms along the way, and we can't lose any atoms along the way, right? The number of atoms that we have, of each type that we have at the start, must be the same number of atoms of each type that we have at the end of the chemical reaction, right? To do a transformation where we lose atoms is possible, but it's not chemistry, that's physics, right? That's sort of nuclear physics and stuff. It's outside of what we're worried about. And so such a chemical equation then, where we have the same numbers of things in the reactants as in the products, is called a balanced chemical equation. And balancing chemical equations and using those is of the utmost importance for everything we're going to be doing for these next few lessons, right? Now, there is not really, that I'm aware of, a hard and fast little algorithm for going about balancing equations. Like I say, we're normally going to give you the balanced equation, but even if we don't, the only sort of system I've come across in books and stuff involves using simultaneous equations, which, I mean, I quite like simultaneous equations, but it seems to me if you don't understand how to balance an equation, doing it with relatively complicated math probably isn't going to help you. So the way to go is to just try things and try putting in some stuff and trying to make it work, right? We're going to talk through some examples of how to do this in a few slides, but don't get too worried about learning how to balance equations, right? Anything that we give you in this course, at least, if it's not already balanced, is going to be very straightforward, hopefully, once we see how we go about doing it, okay? So here now is just to make the point, is to show with some little animations how we can do some chemical reactions, and showing you how this whole idea of things rearranging themselves into new forms but not being lost or gained works, right? So in this first example, we have a carbon atom and we have an O2 molecule, right? So this could be us burning a piece of carbon to make carbon dioxide. Now, like I said, we would probably tell you this, but you can see here in that animation how the oxygen-oxygen bond breaks and we form two new carbon-oxygen bonds in that process, right? Now, in order to make a CO2 molecule, we needed one carbon and we needed one O2 molecule. And so we can write an equation like this to describe that reaction. We can write C plus O2 gives CO2, right? Here's another example. Now reacting carbon atoms with hydrogen gas, right? And what we've drawn here is one carbon atom and two H2 molecules. And when we do this reaction, we find that we can make from one carbon and two H2 molecules one CH4 molecule. Right? So again, the two H2 molecules are coming apart, those covalent bonds between the hydrogens are breaking, and then we're forming new bonds for each of those hydrogens to the carbon, right? And then a third example, here now is a bit more complicated. Now we've got two carbon atoms, we've got four H2 molecules, and we've got an O2 molecule, and we can see that if we mix these together, we can form two CH3OH molecules, right? So this is the formula for methanol. So in this reaction then, we can say that two carbons react with four H2s and one O2 to make two CH3OHs, right? We've got enough carbons in the reactant side to make two, because each methanol only has one carbon in it. Each methanol's got four hydrogens. So in order to make one methanol, we need to have two H2 molecules. If we want to make two methanols, we need four H2 molecules. And to make a methanol, we need one oxygen. And this is where we've got two of everything, right? Because we're starting with O2 gas. And so we're starting with two oxygen atoms in that O2 molecule as our ingredients. They both need to be used, right? Remember, we can't have things left over. So in order for both of them to be used, we need to make two methanol molecules. And if we need to make two methanol molecules, that means we need two carbons and we need four H2s, right? So hopefully you can see how this works. You could imagine you could just write C plus 2H2 plus O gives CH3OH, but you can't just write O because that's not our reactant, right? That's not our ingredient. Our ingredient is O2. And so in order to have a balanced chemical equation, we need to have both of those oxygens being incorporated into methanol molecules, and that in turn means that we need to have two carbons and four lots of H2. Now, if we look at a bit again at this equation we've just written, then we can see, in the same way that we did for our pancakes, that when we're writing out our equation for this, we can specify the numbers of each of these types of atoms or molecules that we need to get to our balanced chemical equation, right? So we can say that we need two carbons plus 4 H2s plus 1 O2 gives 2 methanols. Now these big numbers that we write in front of each of the ingredients, each of the reactants in the products, have a name. They're called stoichiometric coefficients, which is kind of a big name, but it just means, I tend to call them the big numbers out the front, right? And those big numbers are there to tell you about the ratios in which each of the reactants in the products appear in our balanced chemical equation, right? So it's the same idea as when we had our 8 pancakes. To make 8 pancakes, you needed 2 bananas and 4 eggs, right? If you like, the 2 for the 2 bananas is a stoichiometric coefficient, and the 4 for the 4 eggs is a stoichiometric coefficient, right? In our balanced chemical equation, these stoichiometric coefficients are key because they tell us about how many of each of the different types of reactant molecules we need in order to combine them correctly to make our products. And in the same way as we did for our pancakes, once we know what these stoichiometric coefficients are, then we can ask questions like, if I wanted to make 16 methanol molecules, how many carbon atoms would I need? And so we go to our balanced chemical equation, which says that to make 2 methanol molecules, you need 2 carbons. So if you want to make 16 methanol molecules, you'll need 16 carbons, right? If I wanted to make 10 methanol molecules, how many hydrogen molecules would I need? Well, my balanced chemical equation tells me I need 4 H2s to make 2 methanols. If I want to make 10 methanols, then I will need 20 H2s, right? Twice as much, because to make 2 methanols, I need 4 H2s, twice as many molecules. So to make 10 methanols, I'll need 20 H2s, right? Being able to see these relationships between an amount of one thing in your reaction and an amount of something else is the first of these things which sometimes students find quite difficult, right? But it's extremely important for what we're doing going forward. Now, let's say we want to make a certain amount of methanol, right? Let's say we want to make 112 molecules of methanol for some reason. How then do we know how many of the ingredients to put in, right? I mean, we can work out how many we need because we can use our ratios, we can use our stoichiometric coefficients, right? But doing this is a different thing to making 8 pancakes. To make 8 pancakes, we've got to go find 2 bananas, but that's all right. We can go get those from the supermarket or whatever. We can have 2 bananas in our hand and we can go and get 4 eggs and so on. But to make a certain number of methanol molecules is a problem because the carbon atoms and the hydrogen molecules and the oxygen molecules we need to make them with are very small. We cannot count out. Say if we want to make 20 methanols, we would need to have 20 carbon atoms. We can't count out 20 carbon atoms in the way that we can count out 2 bananas because the atoms are too small, right? And so therein lies one of the major issues with doing chemistry, is that we want to be able to use our knowledge of certain chemical reactions to make something in particular and to make a certain quantity of it in particular, but we can never count out how many of the ingredients we need in order to correctly be able to make a certain amount of the product, because the ingredient molecules are too small. And so the solution to this problem is to, rather than counting out a certain number of atoms or molecules, is to in fact instead weigh them, which is fine so long as you know how much a certain number of those atoms or molecules weighs, right? This idea of counting things by weighing them is something that you may have already come across in your experience. Here is a picture of a machine which can count money by weighing it, right? And these machines are quite clever. You find them at the bank, but sometimes you can get them if you've got lots of cash that you need to count very quickly. You can do it the old-fashioned way, but sometimes it's just as easy to put a whole bunch of, say, $2 coins in a bag, tell the machine these are $2 coins, push a button and it tells you how many there are there, because it weighs them and it knows how much one $2 coin weighs exactly. And because the total weight in your bag will be some multiple of the weight of one $2 coin, it can work out how many $2 coins there are, right? And then if you have another bag and you put 50-cent pieces in there, and then you tell it it's 50-cent pieces, it can tell you how many there are in there, because again, the 50-cent piece weighs something different to the $2 coin. And so this idea of counting how many things we have by weighing them is what we do in chemistry, right? We have a way of working out how much a certain number of atoms of a certain type weigh. Then if we weigh the sample, we can work out how many of those atoms are there, right? Just to make the point that we need to do this because we can't really count the atoms. Let's imagine we wanted to make some sulfur dioxide, which seems a bit strange because it's not very nice stuff, but let's imagine we wanted to make some sulfur dioxide, and we're going to do it by taking some sulfur, some elemental sulfur, yellow sort of mineral, crystalline looking stuff, and burning that in oxygen. And let's imagine that we started with a piece of sulfur that weighed 6 grams. And we wanted to know how many SO2 molecules we could make from that. Well, we first of all have to know how many sulfur atoms there are in 6 grams of sulfur. And you can work out, using ideas which we're going to be talking about very soon, you can work out that there are this many sulfur atoms. There's 112,912,500,000,000 atoms. It's a lot, right? You can't really be sitting there counting all of those out in order to be able to work out the exact right number of oxygen molecules to mix with that sulfur to make your SO2, right? You can't, because they're too small and it's too hard. And so now we get to perhaps one of the most important ideas in all of chemistry, certainly all of foundational level chemistry. And that is this idea that rather than talking about amounts of actual atoms or molecules, we can talk about them in groups, right? And we talk about them in groups because, like we say, there is just vast numbers of these atoms or molecules in any sample of stuff that we might want to do a reaction with in the lab, right? And so the group of things that we use is called a mole, M-O-L-E. And a mole just is a way of talking about a certain number of things, right? Be it atoms, be it molecules, be it ions, be it whatever, right? But it has a fixed value. And the fixed value is 6.022 times 10 to the power of 23, right? Now that's not a dissimilar number to the number we just saw for the number of sulfur atoms in 6 grams, right? It's a big number, but it's related to the fact that the atoms and the molecules are very, very, very small. And so in order to have a way to talk about groups of them that's useful to us in a practical sense, that group has to contain a lot of things, right? So 6.022 times 10 to the 23, or if you like, 602,000,000,000,000,000,000,000,000,000,000 things. It's a big number. Sometimes people, when they're talking about moles, talk about it in terms of like dozens, right? So the mole is a word which represents a group of things, a group of a certain size. Dozen is another word in English which means a group of a certain size, right? In the case of a dozen, that group is 12 things, right? Similarly, there's also the word pair, P-A-I-R, which is a word that refers to two things. There's a gross, which is 144 things. If you're familiar with photocopiers and stuff, then we talk about paper for photocopiers in reams. A ream of paper is 500 pieces of paper, and so on, right? We have various words like this to refer to a group of things of a certain number. In chemistry, that word is the mole. And the mole refers to a very large number of things, but nonetheless the idea is the same. Okay. Now, to give you a sense of just how big a mole is, I came across, there's lots of different ways to describe this, but I came across this really nice video just recently, and so I'm going to play that now, and you can see, get a sense for just how many things a mole of things is. Alright, so hopefully that gives you a sense of just how many things there are in a mole of things. And yet, as was kind of indicated in that video, a mole of elements is not actually that big in terms of the piece, of stuff you're talking about, right? This is 1 mole of aluminium, right? It weighs about 27 grams. And it's really not that big at all. It kind of looks like a knob that you'd have on a toaster or something. But this contains 6.022 times 10 to the power of 23 aluminium atoms in this little piece, right? Atoms are small. This idea of the mole then is going to help us with our balanced chemical equations. Because up till now, when we've talked about 2 carbon atoms reacting with 4 hydrogen molecules and 1 oxygen molecule to make 2 methanol molecules, we can also talk about that as being in terms of moles, right? We could say 2 moles of carbon atoms reacts with 4 moles of hydrogen atoms and 1 mole of oxygen atoms to make 2 moles of methanol molecules. Right? We can do that because the big numbers, the stoichiometric coefficients, refer to the relative numbers of things. And that can be 2 atoms or it can be 2 moles of carbon atoms. The ratio is still going to be the same, right? And so this is what we do. Rather than thinking about reactions and being in terms of individual atoms and molecules, we think about them as being groups of atoms, large groups of atoms or molecules reacting with each other. Because, like I say, in any sort of reasonable reaction you might do in a lab or in a factory, you're going to be doing that reaction on these sorts of numbers of things, right? So the mole is a much more useful way for us to think about things rather than thinking about individual atoms. But then we have this problem. Well, if we're going to use a mole of carbon atoms, well, that's only useful to us so long as we know what a mole of carbon atoms weighs, right? This is our weighing out the coins thing, right? If we want to know exactly that we have to add 1 mole of carbon atoms, again, we can't count them out because now they're small, but there's also a heap of them. What we need to know is we need to know what the mass of 1 mole of carbon atoms is. And then we know that if we weigh out that mass, we know how many carbon atoms are going to be in our flask, right? And so to work this out, we make use of the idea of molar mass. The mass of 1 mole of something. And helpfully, the molar masses are on the periodic table, right? And we've possibly already talked about this in an earlier video, but you've certainly probably seen these numbers now. So if we look at the little box for carbon, then above the C, the symbol for the element, there's a 6. And the 6 refers to the atomic number, how many protons a carbon atom has in its atoms. But that's the thing that gives the carbon, the atom, its identity as being a carbon in the first place. But then below the C, there's a number, 12.01. And the 12.01 is the molar mass, right? That's the mass of 1 mole of carbon atoms. And so that means that if you have 12.01 grams of carbon in a test tube or something, then you can say that that contains that the number of atoms in there is 1 mole. It's 6.022 times 10 to the 23 atoms are in that test tube, right? In a similar way, if the box for oxygen has an 8 above the O symbol for the oxygen, which is how many protons there are, and then below it has a number 16, right? And 16 is the molar mass of oxygen. It's 16 grams per mole. So there are 16 grams of oxygen atoms per mole of oxygen atoms. Each mole weighs 16 grams. Right? For sulfur, it's 32.06 grams per mole. And so on. And so we can use our periodic table to be able to relate for any element the number of the mass of a sample that we might have of that element to the number of atoms or the number of moles of atoms there are in that sample. And remember, we need to know that because then that allows us to work out how much of one we have to combine with how much of something else in order for those ratios to be right, in order to make the products in the way that we need to according to the balanced chemical equation. If we know that the molar mass of sulfur is 32.06 grams per mole, and we want to know what the mass of 2 moles of sulfur would be, then hopefully we can see that if 1 mole weighs 32 grams, 2 moles will weigh 64 grams, right? Twice as many atoms will weigh twice as much. And we can express this with a little bit of math, if you like. We can say that the mass of our 2 moles of sulfur will be equal to the amount, the number of moles we're asking about, times the molar mass, capital M, which is the mass of 1 mole. So in this case, we will have the mass of 1 mole times 2, the number of moles we're interested in, and this little bit of math will give us the mass, right? So we can say that the mass of sulfur in 2 moles is equal to the 2 moles times 32.06 grams per mole, the grams in 1 mole, and that gets us 64.12 grams. In the same way, we could say if the molar mass of carbon is 12.01 grams per mole, what is the amount of 18 grams of carbon, right? Now, to be clear, amount refers to moles, mass refers to grams, amount refers to moles. And so this is the way it's going to be from now on. So if I'm talking about the amount of something, that's going to mean the moles of that something, right? And so if we want to know how many moles there are of carbon in 18 grams, when we know that there's 1 mole in 12 grams, now we can write a little bit of math like this. We can say that the amount is equal to the mass that we're interested in divided by the mass of 1 mole of the stuff, right? So N is equal to little m divided by the big M. In this case, it's going to be your 18 grams divided by 12.01, the grams that are in 1 mole, and that's going to give us 1.5 moles, right? So 1 mole of carbon weighs 12 grams, 1.5 moles of carbon weighs 18 grams, and so on. All right? Hopefully this makes sense. And from these little bits of math, we can develop a formula that relates these 3 key ideas for all of these sort of fundamentally important calculations that we're going to do in chemistry, right? A formula that relates the amount of substance there is in a sample, the moles, the mass of the substance, the thing we can actually measure experimentally, and the molar mass, which is the link between the mass and the moles. And so we have a formula which says things like amount is equal to mass divided by molar mass, which is at the middle here. And we can rearrange this to have each of these 3 things as being the subject of this equation. So we can say mass is equal to amount over molar mass. We can say mass is equal to amount times molar mass. We can say amount is equal to mass over molar mass. And we can say that molar mass is equal to mass over amount. Being able to take one of these formulas and then rearranging it to get one of the alternate forms of the equation is an important bit of algebra that you need to get some ability at doing, right? There was an earlier video, I think, that talked a bit about rearranging equations. We don't need you to do extremely difficult math in undergraduate chemistry, really, but you've got to be able to do this stuff, right? Now, for straightforward equations like this one, then sometimes it can be helpful to put them in a triangle, like what we've drawn here, right? And so we remember how the triangle works. So we draw the triangle, we divide it into 3 parts, we put mass at the top, we put amount on the bottom on the left-hand side, and we put molar mass on the bottom on the right-hand side. And then that allows us a way to work out how to do the math, right? So mass on the top is equal to amount times molar mass, because amount and molar mass are beside each other, so we multiply across when things are beside each other. Whereas amount is mass divided by molar mass, because the mass is above molar mass in our little triangle, right? And so on. So sometimes learning these triangles, there's another equation we're going to do in a later video where you can also do a triangle. They don't always work, but for this equation they do, and because this equation is so crucially important to much of what we're going to do for the next few lessons, use this as a way to learn things if you need to, right? And then just finally, before we finish this one, on the right hand side I've put in the units, right? So the unit of mass is grams. So mass is in grams, but the symbol for the unit is G, right? Not grams, not GMS, it's G. This sort of stuff matters if we're going to be all correct and scientific about things. It matters to write the unit symbols correctly, right? So G for grams. Moles, the unit symbol is MOL. Right, it's not MOLES. So if we're writing out we're doing some math and we're writing a number in for an amount, we won't write 1.2 moles MOLES. We'll write 1.2 mole MOL. Right, and similarly, the unit for molar mass is grams per mole, which normally you will see written, at least in chemistry, as being a G and a space and then MOL to the power of -1. So the power of -1 means 2 per mole, right? You could write grams over moles, but you're going to see it this way much more commonly, and so it's probably important to get familiar with this one. you.